Hey guys, this is a quick magnetism overview for physics, and we'll be going over some concepts and doing some example problems for magnetism. So, most materials have paired electrons in opposite directions, and the field created by one electron is cancelled out by another, and this way no magnetic fields are created. But magnetic materials have single electrons or paired up electrons that spin in the same direction, which causes an unbalanced force. And magnets always have two poles, a north pole and a south pole. And the magnetic field goes from the north pole to the south pole. So magnetic fields are created by moving charges, and anytime a charge moves, a magnetic field is created. Magnetic force is created by two magnetic fields occupying the same space, and a magnetic field is defined by any region where another magnet would feel a force. Hand rules are used to remember the arrangement of a magnetic field and force created by a moving charge, and they help you solve magnetism-related problems. And here are the two right-hand rules. You should memorize them. And here's the left-hand rule, and that should also be memorized. Now, magnetic field strength, or B, is a vector which is measured in teslas. The field lines always run from north to south, and the density of the magnetic field is known as magnetic flux, or flux density. Magnetic force is perpendicular to a charged object's velocity, so it can't do work on it. And the equation for magnetic force is F equals BIL, which is B is flux density, I is current, L is length of conductor. You can also write it as F equals B times delta Q over delta T times V times delta T, and you can cancel out the delta T's to write the magnetic force equals QVB. And you can also write it as magnetic force equals QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. The total force on a moving charge is known as a Lorentz force, and the equation for it is Q times E plus V cross B. And you can also see it as the electric force plus the magnetic force, because you can rearrange the equation to make it the total force is equal to the electric force plus the magnetic force. An airplane accumulates an excess positive charge of 2.0 times 10 to the fifth c. What is the magnetic force on the airplane when passing at 240 meters per second through and perpendicular to the Earth's magnetic field, which is 5.0 times 10 to the negative 5t teslas? So now we know the Q and we know the V and we know the B. So we can use, and we know the sine theta because it tells us it's perpendicular, so theta is just 90. So we can see that the magnetic force is equal to QVB sine theta from the equation, and then we plug in those values. So the magnetic force is equal to 2.0 times 10 to the negative fifth. Times 10 to the fifth and times 240 and times 5.0 times 10 to the negative fifth. And then multiplied by sine of 90, which would just be 1. So now we just solve for that. And we get the magnetic force is equal to 2.4 times 10 to the negative 7. So a solenoid is basically an electromagnet that produces a magnetic field in a volume of space when an electric current passes through it. And the strength of it depends on three things: the strength of the current, the number of coils, and the size of the core. And as you get farther away from the center, the magnetic field flow would decrease. So the force would be really weak when you're far away from the center. Ampere's law is a very important law in electromagnetics. It states that the magnetic field times the length is equal to the permeability times the current for a closed loop, and this law can be applied in solenoids and other electromagnets. Faraday's law of induction states how the voltage can be how voltage can be generated using magnets, and it's basically this equation here where n is number of turns, B is magnetic flux, B is magnetic field, and A is the area of the coil. Here's an equation sheet for magnets in case you need it. So a solenoid is used to generate a magnetic field. The solenoid has an inner radius A, length L, and N total turns of Y. A power supply is connected to the solenoid and generates current I, as shown in the figure on the left. The x-axis runs along the axis of the solenoid. Point P is in the middle of the solenoid at the origin, as shown in the cutaway view. Assume L is much greater than A. Select the correct direction of the magnetic field at point P. Well, the direction of the magnetic field at point P would be in the plus x direction, because you can use right-hand rule. Now, on the cutaway view below, draw an Amperian loop with point P at the center. So we could just draw a rectangle here, and that would be our loop. Use Ampere's law to derive an expression for the magnetic field at point P with these constants. So we know that Ampere's law, the equation for Ampere's law is equal to this. Now we know that can just be simplified down to BL. L is the length of it. Now AD and BC are actually 0 because they're perpendicular, and DC is far away, really far away from the center. So we can assume that to be 0 because it's really far away, and the magnetic field is really weak there. So now we can just we just have that is equal to BL. So we know that we can just plug that in. BL is equal to mu naught I. So there's an n total number of turns. So we can say that the I induced is equal to n times I, and the BL will be equal to mu naught IN. And the magnetic field is equal to mu naught IN over L. So a thin conducting loop of radius B and resistance R is placed concentric with the solenoid. The current in the solenoid is decreasing from I to 0. Is the direction of the induced current in the loop clockwise or counterclockwise when it's decreasing? Well, you know the magnetic field is going that way and it's decreasing, so the induced current will want to create a magnetic field to make up for that. So if you use your right-hand rule, you can see that it'll be clockwise. So now derive an equation for the average induced current during the time period when it's decreasing in terms of these. So we know that the voltage, not the voltage, the induced current is equal to the voltage over the resistance, which is RL, that's Ohm's law. Know that the voltage is the negative derivative of flux over time. And we know that the flux is just B times A, which is magnetic field strength times the area. So we know that the magnetic field strength is mu naught times Ni over L. And the A is just the area of the solenoid, which would just be pi A squared. So now we just take the derivative of that to get voltage, and I is the only thing that changes. And the derivative of I is just I over the time it takes to get down to 0. So it'd be 0 minus I over t. And then that would just be negative I. Because 0 minus I would just be negative I. So now we have the voltage is equal to mu naught n pi A squared times the negatives cancel out, so now they're positive, times I over delta t. And now we're looking for the induced current. And we know because of Ohm's law, current is velocity over the resistance, which is RL. So now we just do that and we get the induced current is equal to mu naught times N times pi times A squared times the I over RL times L times delta T. And that's it. Hope this helped.